What is machine learning or modeling? So we will use when we want to select the prediction target, we'll use a dot notation to select the column we want to predict, and it's called the prediction target. By convention, the prediction target is called Y. So the code we need to save, for this example, the house prices in the Melbourne data is Y equal Melbourne data, that price. Choosing features. So the columns that are inputted into our model and later used to make predictions are called features. So in our case, those would be the columns used to determine the home price. Sometimes you will use all columns except the target as features. Other times you will be better off with fewer features. For now, we'll build a model with only a few features. Later on, you will see how to iterate and compare models built with different features. We select multiple features by providing a list of column names inside brackets. Each item in that list should be a string with quotes. Here is an example. And by convention, this data is called X. So let's quickly review the data we'll be using to predict house prices using describe method and the head method, which shows the top few rows. And visually checking your data with these commands, such as x.describe, x.head, they're important part of a data scientist's job. You'll frequently find surprises in the data set that deserves further inspection. Building your model, we will use the scikit-learn library to create the model. When coding, this library is written as sklearn, and scikit-learn is easily the most popular library for modeling the types of data typically stored in data frames. And here are the steps to building and using a model. First is define. In the define step, you want to check what type of model will it be. Is it going to be a decision tree, or are there other type of model and some other parameters of the model type specified too? Then step 2 would be fit. So you would like to capture patterns from provided data. This is the heart of modeling. And step 3 is predict. You want to predict the target variable. And step 4 is evaluate. You want to determine how accurate the model's predictions are. So here is an example of defining a decision tree model with scikit-learn and fitting it with the features and target variable. Many machine learning models allow some randomness in model training. Specifically, specifying a number for random state ensures you get the same results in each run. This is considered a good practice. You can use any number, and model quality won't depend meaningfully on exactly what value you choose. So after this, we now have a fitted model that we can use to make predictions. In practice, you'll want to make predictions for this case, new houses coming on the market rather than the houses we already have prices for. But we'll make predictions for the first few rows of the training data to see how the predict function works. Now we are on model validation. Model validation, you want to evaluate almost every model you ever build. in most applications, the relevant measure of model quality is predictive accuracy. In other words, the model's predictions be close to what actually happens. So you first need to summarize the model quality into an understandable way. So if you compare predicted and actual home values for 10,000 houses, you'll likely find mix of good and bad predictions. So looking through a list of uh, 10,000 predicted and actual values would be pointless. We'll need to summarize this into a single metric. There are many metrics for summarizing model quality, but we'll start with one called mean absolute error. Let's break down this metric starting with the last word, error. The prediction error for each house is actual minus predicted. So if a house cost 150,000 and you predicted it would cost 100,000, the error is $50,000. With the mean absolute error metric, we take the absolute value of each error. This converts each error to a positive number. We then take the average of those absolute errors. This is our measure of model quality. In plain English, it can be said as, on average, our predictions are off by about X value. So this is the code example. Here's how we calculate the mean absolute error. The measure we just computed can be called an in-sample score. We used a single sample of houses for both building the model and evaluating. Here's why this is bad. This value 434. So the problem with in-sample scores, so let's imagine in the large real estate market, door color is not related to home price. However, in the sample data you used to build the model, all homes with green doors were very expensive. The model's job is to find patterns that predict home prices. So it will see this pattern and it will always predict high prices for homes with green doors. Since this pattern was derived from the training data, the model will appear accurate in the training data. But if this pattern doesn't hold when the model sees new data, the model would be very inaccurate when used in practice. Since models' practical value come from making predictions on new data, we measure performance on data that wasn't used to build a model. The most straightforward way to do this is to exclude some data from the model building process and then use those to test the model's accuracy on data it hasn't seen before. This data is called validation data. The scikit-learn library has a function train test split that would break up the data into two pieces. We'll use some of that data as training data and to fit the model, and we'll use the other data as validation data to calculate mean absolute error. Now that we have a way to measure model accuracy, we can experiment with alternative models and see which gives the best prediction. So recall from the decision tree lesson that a tree's depth is a measure of how many splits it makes before coming to a prediction. This is a relatively shallow tree, the example you see. In practice, it's not uncommon to see a tree that have 10 splits between the top level and a leaf. As a tree gets deeper, the dataset gets sliced up into leaves with fewer houses. If a tree only had one split, it divides the data into two groups. If each group is split again, we would get 4 groups of houses. Splitting each of those again would create 8 groups and so on. So now we need to talk about overfitting. So when we divide the houses amongst many leaves, we also have fewer houses in each leaf. Leaves with very few houses will make predictions that are quite close to those homes' actual values, but they may make very unreliable predictions for new data. Why? Because each prediction is based on only a few houses. So now underfitting. So since we care about accuracy on new data, which we estimate from our validation data, we want to find the sweet spot between underfitting and overfitting. So visually, we want to get to the low point of the validation curve, which is in red in the figure here. And this is an example of predicting and calculating mean absolute error. And then it compares mean absolute error with differing values of max leaf node. And we can see that the mean absolute error value decreases as max leaf node increases. And then after max leaf node hitting 500, we'll see that mean absolute error increases.